Okay, so for number 4, we have this air gap parallel plate capacitor, initially with a charge of Q, and then we double the separation between the plates and shove a dielectric in there, and we want to determine the factor by which the energy stored in the capacitor changes. And the implied situation here is that this is not hooked up to a power source. So we really just have, here we have this this capacitor, and we can say the plates have an area A and a separation of D, and they've got some charge on them. It's storing a charge Q, which means there's Q on this side, positive Q on one side, and negative Q on the other. Okay, and of course there's some voltage. The capacitor is disconnected, so these lines don't go off anywhere. They just they're like wires that are disconnected, the little wires hanging out the side of a capacitor. Okay, so what happens is first you double D, and then 2 we insert dielectric with a constant of kappa. Okay, and we want to find the change in energy. So find change in energy stored. Okay, so the energy stored in a capacitor, this is something we derived in class. Energy stored in a capacitor, energy stored in a capacitor is 1/2 the charge on the capacitor times its voltage. There we go. That is the energy stored in a capacitor. Now, we don't have the voltage here. We can find it if we want, but here's the thing. We can actually rearrange this using Q equals CV, our basic capacitor equation, and get this here in terms of C. And let's see, what do I want to do? Actually, what I want to do is take this and turn it into V equals Q divided by C, and then plug this in for V. So then you get the energy stored as 1/2 Q squared divided by capacitance. Okay, and then you're all set, right? So in this case, for a parallel plate capacitor, the capacitance here for this guy, okay, capacitance is just standard for a parallel plate capacitor filled with air, A epsilon naught, come on, 0, there we go, over D. And then we plug that in there, and we can put this all together and say the charged or the stored energy is 1/2. Come on, I can do this. This is just algebra. Well, our actual charge, they used big Q, so I'll plug in big Q for little q. Q squared over A epsilon naught over D, so the D comes up there. So that is the initial value for energy stored. Okay, now after all this stuff is done, the capacitance, first of all, if you double D, so I'm going to say, this is a slight abuse of notation, but I'm going to say we're going to take our original D, and the new capacitor has a plate separation of 2D, so there's your capacitance, 2D, or A epsilon naught over 2D, sorry. And then after you insert the dielectric with a dielectric constant kappa, you multiply the whole capacitance by that, sorry. So this, there we go, this is our new capacitance. Excuse me just a second. Okay, sorry, I had to cough. Alright, so I didn't want to do it on the mic, you know. Because then you guys might get sick. So anyway, we can plug in our new capacitance into here, okay? And the thing is, so I'm going to take this again, and I know I'm drawing a lot of lines here, but hope you can follow. So capacitance here, we're going to keep the same charge on it. That's really the key to several of these problems, is recognizing that when a capacitor is disconnected from a power supply, the charge just stays the same. There's no place for it to go. So the Q squared, and then over C, so we divide this by our new capacitance, which is kappa A epsilon naught over 2d. So then, of course, that comes up. And so let's see then what that ends up being. And so I want to sort of pull out this thing here out of this so we can see clearly what it is. So the 2 and the kappa are what's different. So 2 over kappa times 1/2 q squared d over a epsilon naught. Okay, so now, if you can read my horrible handwriting, you can see this here, this original capacitance, or sorry, not original capacitance, original energy stored is, this is all the after stuff, is right in here. So the factor by which this is changed is 2 over k, which I believe was what they asked for, right? Number 4. The factor by which the energy stored in the capacitor changes. So that factor is 2 over k. Okay, easy enough.